Hey, good morning, physical science students. Today is day 2 of Unit 5C, which is nomenclature and bonding. Today we're actually going to get into ionic bonding and ionic nomenclature. So nomenclature is just a fancy way of saying naming and writing formulas. We have a specific set of rules. They are the International Union of Pure and Applied Chemistry, or the IUPAC rules, that we have to follow when we name and write compounds. For physical science, we are focusing on only binary compounds. Binary compounds means two elements, hence bi. So it has two elements that make up the compound. We do not look at anything that contains, in terms of nomenclature, polyatomic ions. So, starting off with just some basics for our ionic bonding ionic nomenclature. When we're looking at a chemical formula, the chemical formula shows us two pieces of information. First and foremost, it shows us the number of elements in the compound as well as the ratio of their atoms. So water is a covalent compound because it contains two nonmetals, and I can see that it has two hydrogen atoms and one oxygen atom. Now, chemists tend to be lazy and we don't write ones. As a beginning chemistry student, if you want to write the ones as a subscript to indicate that there is only one atom, you're welcome to. See something else. Let's say I have Al2S3. So this is an ionic compound because it has a metal and a nonmetal. And I can see that based on its formula, it has two aluminums and three sulfurs. So that chemical formula gives us a lot of information about the compound. Now, a chemical bond is just the strong attractive force between the atoms or ions in a molecule or a compound. Now, chemical bonds can be formed by transferring electrons. We see this when we have our metals who lose electrons and giving them to our nonmetals who gain electrons and form that anion. Metals losing their electrons, forming that anion. That is called an ionic bond when it is formed by the transfer of electrons. Bonds can also be formed by sharing electrons. We tend to share electrons between nonmetals. So between two nonmetals, those are our covalent bonds. Now, an ionic bond is formed due to the transfer of the electrons and the fact that we end up with two oppositely charged particles. Those two particles are going to attract. The opposite charges, remember back to earlier in this year, opposite charges attract. That attraction forms an extremely strong bond. Our ionic bonds always contain a positively charged metal and a negatively charged nonmetal. Now, because they are very strong bonds, ionic bonds tend to have very high melting and boiling points. They are good conductors of electricity when melted or if dissolved in water. So as their normal solid state, they don't conduct electricity, but if we melt them or if we dissolve in water, they actually are pretty good conductors. Now, when ionic bonds form, they come together and forms these really pretty 3D structures called a crystal lattice. Every compound has its own unique structure, but they actually form some really interesting shapes and crystals. Because of the strong attractions, we end up with our ionic compounds tending to be solids at room temperatures. So this would be illustrating sodium chloride, where chlorine is the green one and sodium is the gray one. Because chlorine has gained electrons, its cloud's going to be a bit larger than sodium, who has lost electrons and dropped down in energy level. The metal sodium will lose its electron from the outer energy level. Remember that outer energy level are the valence electrons. We know that it's only one valence electrons because sodium is in group 1. So it will give up its single electron to the nonmetal chlorine. the nonmetal chlorine will gain that one electron, forming an anion. You're going to end up with a positively charged sodium and a negatively charged chlorine, and because of those oppositely charged particles, they're going to be highly attracted to each other and will form an extremely strong bond. Oh. Now, generally when we're actually looking at the ion parts, I will not always show the dots, but it is important to notice that sodium has no dots because it has lost its valence electrons. It has lost its outer energy level. Chlorine now has its octet. It has 8 valence electrons. They're both stable because sodium dropped down in energy level. Chlorine filled it up. They have those opposite charged, which forms that attraction called the ionic bond. Now, the chemical formula between this is just NaCl. And you probably know this as table salt, but a scientist would call this sodium chloride. Oops. So, table salt, the stuff that you put on your french fries, is called sodium chloride. Notice how the names and the elements relate. So let's look at a different example. I have calcium, who has 2 valence electrons, and phosphorus, who has 5 valence electrons. So notice that calcium only has 2 electrons to give away, and phosphorus needs 3. Well, that means I'm going to need more calciums in order to balance out, or in order to stabilize the phosphorus. So when we're trying to figure out the charge that each has, we can do that by looking at the number of electrons that it gains or loses. Now, when you're going to figure out the formula, there is called the crisscross method. I call it swap and drop. Crisscross, it's the same idea. It's where you take these charges and you swap them over to get the formula. Because all ionic compounds are neutral, the resulting formula must result in a neutral compound. So the chemical formula is Ca3P2. This is showing me that it requires 3 calciums to balance out the 2 phosphoruses. And we could kind of see that if we just look at the charges. So if I had one of each, I would have a negatively charged substance. That's not allowed. Ionic compounds and all compounds are neutral. Well, if I had 2 calciums and 1 phosphorus, now I have a positively charged thing because I have 4 positives and -3. So let's add another P. Well, now we're negatively charged. We've got 6 negatives, 4 positives. So let's add another positive. Now we get to the point where all of my ions add up to equal a neutral charge. This is why it takes 3 calciums to balance out 2 phosphoruses. The crisscross method or the swap and drop method is nice because you don't really have to do the math. You just look at those ions and you swap and drop. The charge, the positives and the negatives cancel out, so they disappear. And I'm holding the wrong periodic table. So let's look at one more example. So let's say I have Mg, who's a +2, and O, who's a -2. And I do this example on purpose because this is one of the times where crisscross will not result in the same answer, or in the correct answer. Because those charges automatically cancel out, I don't need to swap and drop them. I literally just need to write 1 Mg to 1 O. Now, we don't see this happening very often in physical science, but if ever your charges are the opposite charge but the same number, you just have to write the letters as your subscript. If we change elements, then we're going to end up changing the formula. So let's say I'm doing magnesium and chlorine. They don't cancel out, so I swap and drop. My formula is MgCl2. And if you really, really wanted to, you could put that 1 beside the Mg. It's just Miss Raines is a lazy chemist, and I tend not to write the 1s, but you can if you want. So it is important to note that the subscript does not have a positive or negative sign. We cannot have a charged particle in a compound. Compounds are always neutral. So those positives and those negatives cancel out. We saw that with the example of the calcium and the phosphorus. The positives and the negatives cancel out, so they just disappear. So, another example, this one is calcium and bromine. Calcium has a +2 charge, bromine has a -1 charge, so we end up with Ca1Br2. Now, again, I don't care if you write the 1s, I'm not going to because I'm going to be a lazy chemist. One other thing I want to point out is notice the name of this compound, calcium bromide. Calcium bromide. We are seeing an IUPAC rule being used before we've actually learned the rules. So, in terms of our nomenclature rules, the first element tends to keep its name. Whatever it is, the first element keeps its name. The second element, we write the first part of the element's name, and then we replace the ending with IDE. That's how we get calcium bromide. So let's look at a couple of examples of writing ionic formulas. Now, for these examples, I'm going to give you the name, and you have to go to the compound. Now, when I give you the name, you want to write, bad Miss Raines, I'm asking you to get the name from the formula. So we're trying to get our name from our formula. The first thing you got to do is just look at the names of the elements. Your metal is always written first. That is our general rule. Most metallic element is written first. That works with both ionic and covalent. Most metallic elements are the elements that are on the left side of the periodic table. So my metal is written first. It keeps its name. The non-metal is written second, and its ending changes to IDE. General rule of thumb is most non-metals keep that first syllable and then replace everything else with IDE. So oxygen becomes oxide. Iodine becomes iodide. There's a few weird exceptions. I'm not stressing about the exceptions. Little spelling errors, not going to count off. But main thing is that you have to replace that ending. So chlorine-ide is not an acceptable name for that non-metal. Nitride is acceptable. Nitrogenide, not acceptable. That ending gets erased and replaced with that IDE. So these three examples, notice I'm giving you the symbols. I'm giving you the chemical formula, and I'm asking you for the name. So look at your periodic table. You do not need to memorize these. Your salmon-colored periodic table has the names of all the elements. You do need to remember to change the ending of the second element. So NaBr, well, Na is sodium, Br is bromine, but bromine becomes bromide. So sodium bromide. Na2S, Na is sodium, S is sulfur, sulfur, I keep the sulf, and replace the ending with IDE. So sulfide. And I don't know why my clicky is out of order, but AlCl3, Al is aluminum, Cl3 is chlorine, it would be aluminum chloride. There we go. So notice we're, for the most part, keeping the first syllable of the element's name. Like in sulfide, if you accidentally left off the F, I'm not going to dock you points. Might fix it, but it's not a big deal. Especially considering we're just barely learning how to write our names and formulas. So that's to get the names from the letters. Well, we have to also be able to go backwards. We have to be able to get the formula from the name. And getting the formula from the name does require a little extra step. So we have to use the name to determine the elements. Once you figure out what elements you're looking at, write the ion that each one forms based on its position on the periodic table. Then crisscross or swap and drop those ions to get the subscript for the other element. Now, of course, this is only if the ions don't cancel. I don't know why I put an apostrophe ions. Don't cancel. If they do happen to cancel out, then you just write the elements. You don't have any subscripts. So let's look at a couple examples. Potassium. This actually is a good opportunity for me to remind you of a really neat feature for the PDF copy of our periodic table. Alrighty. So if you look at the copy of the periodic table that doesn't have the formula sheet, the one that's nice, pretty color-coded, and you're trying to quickly find elements on it, remember the ability to find things. So you bring up the PDF copy and you hit Control F, so hold down Control, hit F, and it will pop up a little box for you to type in part of the name. That was not the button I wanted to hit. There we go. So Control F. So I want to find potassium, P-O-T-A-S-S. I don't even have to type in the full thing. I just type in part of it, and when I hit enter, it will highlight it in green for me. So that lets me know that potassium is K. K is in group 1, and you have to know that everything in group 1 forms a +1 ion. So chloride, well, that ending changed, so it's not going to help me any. So I'm going to look for the element that begins with chlor. Bring up my periodic table, come over here and delete the potass, and type in chlor, C-H-L-O-R, hit enter, and it jumps to the right side of the screen and highlights it in green. So chlorine became chloride. Well, chlorine is in group 17, and everything in group 17 forms a -1 charge. So those charges cancel out. They automatically balance each other. So all I have to do is I just have to write the elements' symbols. So the chemical formula for this compound would be KCl. Alrighty. Magnesium nitride. So magnesium, if we look at our periodic table, magnesium is in group 2, so it forms a +2 charge. Nitride, again, I'm not going to find nitride, but I will find nite. And, oh, it would help if I didn't put the E. I put an R. But anywho, type in nite, and I see that it highlights nitrogen. Nitrogen is in group 15. Group 15 forms a -3 charge. Mg +2, N -3. So these charges do not cancel. They do not balance each other out, so I must swap and drop. I must crisscross my exponent to become the subscript on the other thing. So I'm going to end up with a 3 beside the Mg. And I'm going to end up with a 2 beside the nitrogen. The chemical formula is Mg3N2. That is magnesium nitride. All right. You try the next one using your periodic table. Give it a try. So aluminum is in group 13. Aluminum forms a +3. Oxide, well, I don't see oxide on the table, but I do see oxygen. So oxygen is in group 16. 16 forms a -2 charge. Those charges do not cancel out. They do not balance each other, so we swap and we drop, and we get Al2O3. That 2 came down here. That 3 came down there. And the positives and the negatives canceled each other out. That is how we go from the name to the formula. So make certain that you are doing your practice in Google Classroom. I think if today is a live day, we'll have some breakout rooms available to you. If it's not a live day, then make certain you hop into my office hours for some extra help as needed. Thank you and have a fabulous day.